13.8 billion years ago, an impossible event occurred. Our entire universe erupted from a region smaller than a proton, launching time, space, and all of physical reality into existence. But cutting-edge physics has revealed something that changes everything we thought we knew. The Big Bang wasn't the beginning. Before that cosmic explosion, something far stranger than emptiness existed, a quantum realm buzzing with energy, a place where the fundamental laws of physics were taking shape. We're about to explore colliding dimensions, endless cycles of creation and destruction, and discover why nothing might actually be the most powerful force in existence. Let's uncover how reality created itself from the impossible. Part 1. The illusion of empty space. Imagine the most isolated region of space conceivable. No stars, no planets, no light, just void stretching forever in all directions. Scientists have discovered that this emptiness is a complete lie. When physicists examined the vacuum of space using quantum mechanics in the mid-20th century, they found something shocking. Empty space isn't empty at all. It's seething with measurable energy at every point. Think about the ocean's surface on a windless day. From a distance, it looks smooth and motionless. Move closer and you'll see tiny ripples and disturbances constantly appearing and vanishing. The quantum vacuum behaves identically, except these ripples are invisible energy fields that exist everywhere, always. This discovery has confirmed science, proven in laboratories across the world over decades of experimentation. The vacuum carries what physicists call zero-point energy, the lowest possible energy state that still contains real measurable power. You can't eliminate it, you can't turn it off. It's woven into the fabric of reality at the most fundamental level. Here's where it becomes truly bizarre. This energy doesn't just sit there passively, it actively shapes our universe. In 1948, Dutch physicist Hendrik Casimir predicted that when two metal plates are placed extremely close together in a vacuum within nanometers of each other, they should be pushed toward one another by an invisible force. This prediction was confirmed experimentally. Scientists call this the Casimir effect, and it's been measured with extraordinary precision using modern techniques. The vacuum between the plates contains less energy than the vacuum outside them, creating an imbalance that generates real physical pressure. Scientists have measured forces as small as a few piconewtons, confirming the vacuum's energy structure. This means what we call nothing has properties, it has structure. It can be measured, manipulated, and studied in controlled experiments. Ancient Greek philosophers like Aristotle believed that if you removed all matter from a space, you'd have true nothingness. Modern physics proves they were fundamentally wrong. True nothingness is forbidden by the laws of nature. The implications are profound. If the vacuum has energy, then nowhere in the cosmos is truly empty. Every cubic centimeter of space contains this baseline hum of quantum activity. When you wave your hand through the air, you're moving through an ocean of invisible energy that existed before the first star ignited 13 billion years ago and will persist after the last one dies, trillions of years from now. But measuring this energy created a problem that haunts physicists today. When they calculated how much energy the quantum vacuum should contain based on quantum field theory, the numbers exploded to absurd levels. The predicted value came out roughly 1,020 times larger than what we actually observe, a discrepancy so enormous it's called the cosmological constant problem or the vacuum catastrophe. Imagine predicting someone weighs 10 pounds, then discovering they actually weigh less than a single atom. The gap is that astronomical. This crisis reveals something profound. We don't fully understand what nothing really is at the deepest level. The vacuum hides secrets that could explain the birth of everything. Part 2. Particles from the void. The quantum vacuum doesn't just hold energy, it spontaneously creates matter. Right now, in the space between your eyes and this screen, subatomic particles are materializing from nowhere. They exist for fractions of a second, then vanish back into the void. Scientists call them virtual particles, and their existence has been confirmed through experiments that measure their effects with stunning precision. Here's how they work based on established quantum field theory. Energy and matter are interchangeable, as Einstein showed us with EMC². The vacuum contains energy, and that energy constantly fluctuates due to quantum uncertainty. For the briefest instant, typically around 10^21 seconds or less, a fluctuation can become massive enough to split into a particle and its antimatter twin, an electron and a positron for example, or a quark and an antiquark. These pairs erupt into existence, live for a time span far shorter than you can imagine, then collide and annihilate each other. The energy returns to the vacuum. The cycle repeats endlessly, trillions upon trillions of times every second in every cubic inch of space. The vacuum isn't calm, it's a furious storm of creation and destruction happening at scales far below anything we can see directly with even our most powerful microscopes. Yet we know these virtual particles are absolutely real because they leave measurable fingerprints. In 1947, physicists Willis Lamb and Robert Rutherford noticed something peculiar about hydrogen atoms. The energy levels of electrons orbiting the nucleus didn't quite match theoretical predictions from the Dirac equation. The discrepancy was tiny, about 100 megahertz in frequency, but it was definitely there and reproducible. After intense theoretical investigation, physicists realized virtual particles were responsible. These ghost particles briefly interact with the electron as they pop in and out of existence, shifting its energy by a small but measurable amount. Scientists call this the Lamb shift, and its discovery earned Lamb the Nobel Prize in Physics in 1955. It proved conclusively that the vacuum isn't passive, it's alive with quantum activity. The evidence gets even more convincing. Virtual photons, particles of light that blink in and out of existence, create a phenomenon called vacuum polarization, first calculated by Hans Bethe and others in the 1940s. They briefly screen the electric charge of particles, affecting how electromagnetic forces behave at quantum scales with effects measurable to 9 decimal places of precision. Without virtual particles, the entire mathematical framework of quantum electrodynamics would collapse. They're not optional curiosities, they're fundamental to reality. Think about what this means for the question of nothingness. If the vacuum spontaneously creates matter, even for microseconds, then absolute nothingness is physically impossible. Nature won't allow it. The universe has a baseline level of chaos built into its foundation by the laws of quantum mechanics. But here's the unsettling question. If virtual particles can appear from the vacuum for tiny fractions of time, what prevents a bigger fluctuation from happening? What stops the vacuum from creating something permanent, something that doesn't disappear? The answer involves a principle discovered in 1927 that makes nothing even stranger than you can imagine. Part 3. The uncertainty principle. In 1927, German physicist Werner Heisenberg discovered a rule that fundamentally breaks our common-sense understanding of reality. The Heisenberg uncertainty principle states that you cannot know both the exact position and exact momentum of a particle simultaneously. The more precisely you measure one property, the less you can know about the other. This isn't a limit of our measurement instruments or experimental technique. It's a fundamental property of nature itself, encoded in the mathematics of quantum mechanics. The universe itself doesn't allow certain types of information to exist simultaneously. The mathematical expression is dl x text dl p t hill is the reduced Planck constant, approximately 1.054 text 10^34 joule-seconds. Now apply this principle to energy and time. The uncertainty principle also states that energy can fluctuate wildly, as long as it happens fast enough. The relationship is d text dl t hill is the chu. The shorter the time interval, the larger the energy fluctuation that's permitted by the laws of physics. This is precisely why virtual particles can exist. The vacuum borrows energy to create them, then returns it so quickly that the universe's accounting books balance out. A particle-antiparticle pair with mass m can exist for a time roughly t(nl). Here's the crucial insight confirmed by decades of experiments at facilities like CERN and Fermilab. The uncertainty principle guarantees that the vacuum can never be completely still. There will always be fluctuations, always, forever. You cannot have a state of perfect nothingness, because that would require knowing the exact energy at an exact time, which nature fundamentally forbids. Imagine trying to photograph a hummingbird's wings mid-flight. Your camera captures motion blur because the wings move too fast for a clear image. The quantum vacuum is similar, except instead of motion blur, you get energy blur. The vacuum fizzes with possibilities that never quite settle into stillness. This has staggering implications for cosmology. If there was ever a state of true nothingness before the universe existed, the uncertainty principle would immediately destroy it. Quantum fluctuations would appear spontaneously. Energy would emerge from the uncertainty itself. The void would become inherently unstable. Scientists measure this instability in laboratories today, when they cool systems down to temperatures near absolute zero, FINEV 273.1, 5 kelvins or 0 Kelvin, the coldest possible temperature. Quantum fluctuations become the only motion left. atoms still jitter with zero-point motion, electromagnetic fields still oscillate at their minimum energy. Experiments with Bose-Einstein condensates cooled to billionths of a degree above absolute zero still show quantum fluctuations. You can remove thermal heat, you can remove particles, you can remove classical light, but you cannot remove the quantum uncertainty that makes the vacuum perpetually restless. This isn't speculation or philosophical musing. Teams of physicists have detected these fluctuations directly by studying how light behaves in carefully controlled experiments. They've measured the vacuum's random electric fields affecting electrons with precision instruments. They've observed the spontaneous emission of photons from atoms triggered purely by vacuum fluctuations. The evidence is overwhelming and has been replicated thousands of times. The uncertainty principle creates a paradox when we think about the origin of everything. If absolute nothing cannot exist because quantum laws prevent it, then something has always existed. Either the universe is eternal, or it emerged from a quantum state that was never truly empty. But there's a third possibility that sounds like science fiction yet might describe actual reality. Part 4. The metastable vacuum. Imagine standing on a frozen lake in winter. The ice looks solid and safe, but beneath the surface the water is warmer than it should be, and the ice exists in an unstable state, metastable, waiting for the right trigger to collapse into a lower energy configuration. The vacuum of space might be exactly like that frozen lake. According to quantum field theory, confirmed through decades of particle accelerator experiments, the vacuum can exist in different energy states. There's a true vacuum, the absolute lowest energy possible, and false vacuums that sit at higher energy levels but remain stable for long periods, possibly billions of years or more. Our universe might currently exist in a false vacuum. This possibility terrifies some physicists. Here's why. A false vacuum is metastable by definition. It can suddenly decay into a true vacuum state if the right quantum fluctuation occurs, similar to how supercooled water can instantly freeze when disturbed. When vacuum decay happens, a bubble of true vacuum forms at some random point in space and expands outward at the speed of light, transforming the structure of space itself. Everything caught in the expanding bubble gets restructured at the quantum level. The laws of physics change. The masses of particles shift. The strengths of forces alter. Matter as we know it would cease to exist in its current form. This sounds catastrophic, and it would be for us, but flip the perspective and you get something remarkable for understanding cosmic origins. What if the universe itself started as exactly this kind of event? What if before the Big Bang there was a false vacuum that decayed into our reality? This theory has serious mathematical support through solutions to the Wheeler-DeWitt equation, which describes how quantum states evolve in gravitational and cosmological contexts. Chinese physicists Dongshan He, Dongfeng Gao, and Qingyu Cai published research in Physical Review D in 2014 showing that solutions to this equation permit a tiny bubble of vacuum to appear spontaneously from quantum fluctuations. Under specific conditions in their calculations, this bubble doesn't immediately collapse as you might expect. Instead, it inflates, expands exponentially, and creates a universe. The false vacuum that preceded our cosmos would have been incredibly small, smaller than an atom, possibly as tiny as the Planck length, which is about 1.616 10^435 meters. At that scale, space itself becomes grainy and discrete. Quantum mechanics dominates everything. The usual rules about cause and effect break down completely. At quantum scales, events can happen without prior causes. Fluctuations can create structure from pure randomness. This is confirmed physics observed constantly in particle physics experiments. Particles tunnel through barriers they classically cannot cross. Quantum systems jump between states without continuous transition. Extrapolating these quantum behaviors to the origin of the entire universe requires a significant conceptual leap, but it's a leap firmly grounded in established, experimentally verified science. The metastable false vacuum gives us a concrete picture of pre-Big Bang reality. There was no swirling gas, no primordial matter, no time ticking forward in a conventional sense. There was only a quantum vacuum state hovering in an unstable configuration waiting for the fluctuation that would birth everything we know. Part 5. Vacuum energy and gravity. Energy has weight in Einstein's universe. It curves spacetime, and the vacuum's energy is no exception. Einstein's equations of general relativity, published in 1915, tell us that both mass and energy create gravitational fields. A ball of gas creates gravity. So does a beam of light. So does the energy permeating the vacuum itself. Even though vacuum energy is spread across empty space rather than concentrated in objects, it still curves spacetime. This prediction has been tested and confirmed in multiple independent ways over the past 25 years. The vacuum energy manifests as what Einstein originally called the cosmological constant, a number, denoted by the Greek letter lambda la, that describes how much energy exists in each cubic meter of empty space. For decades after Einstein introduced this concept in 1917, scientists assumed the cosmological constant was exactly zero. They had no observational reason to think otherwise. They were spectacularly wrong. In 1998, two independent teams of astronomers made an observation that shocked the entire physics community. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, measured distant supernova exploding stars that serve as cosmic distance markers and discovered something that seemed impossible. The expansion of the universe is accelerating. Galaxies are flying apart faster now than they were billions of years ago. This contradicts everything physicists expected. Gravity should slow expansion down. Matter attracts matter through gravitational force. The universe should be decelerating, possibly even beginning to contract. But the data showed exactly the opposite trend, with high statistical confidence. Something was pushing space apart with increasing strength. The only explanation that fits the mathematics is vacuum energy. Empty space carries a small but tungo amount of energy density, approximately 6×10⁻10 joules per cubic meter. And this energy has a weird property. Unlike anything else in physics, it creates repulsive gravity. Instead of pulling things together like normal matter and energy, vacuum energy pushes them apart. Even stranger, as space expands, more vacuum gets created, which generates more repulsive force. It's a runaway process that accelerates over time. Scientists call this mysterious component dark energy, and current measurements show it comprises about 68% of the total energy content of the universe. Think about that staggering fact. More than 2/3 of reality consists of the energy of empty space. Regular matter, stars, planets, gas, dust, everything we can see with telescopes, contributes less than 5% of the universe's total energy. The remaining 27% is dark matter, another mysterious component that interacts only through gravity. This discovery completely transformed cosmology in the late 1990s. The vacuum isn't a passive stage where cosmic events happen. It's an active participant that shapes the evolution of the entire universe. It bends space-time. It affects the paths of light rays across billions of light years. It determines whether the universe will expand forever or eventually collapse. The measurements have been refined and confirmed through multiple independent methods. The Planck satellite, which operated from 2009 to 2013, mapped temperature fluctuations in the cosmic microwave background radiation and confirmed the amount of dark energy with incredible precision to within about 1% uncertainty. Ground-based telescopes conducted massive galaxy surveys, measuring how hundreds of thousands of galaxies cluster across space. These surveys, including the Sloan Digital Sky Survey and the Dark Energy Survey, found perfect agreement with the Planck results using completely different techniques. Multiple independent methods converge on the same answer with remarkable consistency. Empty space has power. Real, measurable, universe-shaping power. And this raises a profound question. If vacuum energy can dominate the entire cosmos today, accounting for 68% of everything, what could it have done in the first moments after creation? The answer leads us to the most important event that happened before the Big Bang. Part 6, Cosmic Inflation. Everything you've been told about the Big Bang needs a major update. The hot, dense fireball that forged the first atomic nuclei and released light across space wasn't the beginning of our universe. It was the aftermath of something else, an event called cosmic inflation. Inflation theory, developed in the early 1980s primarily by physicists Alan Guth at MIT and Andre Linde at Stanford, describes a period of exponentially fast expansion that occurred before the traditional Big Bang. During inflation, the universe doubled in size repeatedly in an incomprehensibly short time. We're talking about expansion faster than light, faster than anything the laws of physics normally allow under special relativity. But general relativity permits space itself to expand at any rate, even exceeding light speed. Here's the key point confirmed through astronomical observations. Inflation solves fundamental problems that the standard Big Bang model cannot explain. Problem 1. The universe is remarkably uniform. Galaxies separated by billions of light years on opposite sides of the observable universe have essentially the same temperature, 2.725 Kelvin in the cosmic microwave background, the same density, the same properties. How did regions of space that could never have communicated with each other, that are causally disconnected, become so similar? The old Big Bang model had no answer. The regions were always too far apart to exchange information or reach thermal equilibrium. Inflation provides an elegant solution. If the universe started much smaller than the standard model suggested, then inflated to enormous size in a fraction of a second, those distant regions were once close neighbors. They were in contact. They reached the same temperature and density. Then inflation stretched them across opposite sides of the observable cosmos faster than light could reconnect them. The evidence comes from the cosmic microwave background, ancient light released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. When scientists mapped this radiation across the entire sky using satellites like COB, 1989 to 1993, they found tiny temperature variations of about 1 part in 100,000. The pattern of these hot and cold spots matches inflation predictions with stunning accuracy. The variations look exactly like what you'd expect if quantum fluctuations during inflation were stretched to cosmic scales and imprinted on space itself. But here's what makes inflation truly revolutionary for understanding cosmic origins. Before inflation happened, the universe was cold and nearly empty, not hot and dense. This is the critical insight. The inflationary epoch was driven by vacuum energy, the same type of energy we discussed earlier. This vacuum energy, associated with a hypothetical quantum field called the inflation field, caused space to expand exponentially. Think about the classic example of exponential growth, a chessboard with pennies doubling on each square. Start with 1 penny, then 2, then 4, then 8. By the 40th square you'd be extraordinarily wealthy. Inflation involved at least 60 to 80 doublings, possibly hundreds more. A region smaller than a grapefruit, perhaps as small as 10^26 meters, expanded to a size larger than our currently observable universe, which is about 93 billion light-years across. All of this happened in less than 10^32 seconds. When inflation ended, when the inflation field finally rolled down to its minimum energy state, the vacuum energy that had powered exponential expansion didn't just disappear into nothing, it transformed. The energy dumped into space, converting into a flood of particles and radiation through a process called reheating. This transformation was the Big Bang, as traditionally understood. The heat, the density, the primordial soup of matter, all of it came from the decay of the inflationary vacuum energy. So the correct timeline looks like this. First, a cold vacuum energy state. Second, exponential inflation lasting perhaps 10^32 seconds. Third, the energy converts to hot matter and radiation. That conversion is the Big Bang you've heard about your entire life. Inflation came before. The question becomes sharper and more precise. What came before inflation itself? Part 7. The scale of inflation numbers can be profoundly deceptive. When scientists say the universe doubled in size 60 to 80 times during inflation, it might sound almost modest. It absolutely is not. Each doubling multiplies the size by a factor of 2. 60 doublings mean multiplying by 260, which equals approximately 1.15 10 18 18, more than a quintillion. 80 doublings yield 280, which is about 1.2 10 18 80. The universe expanded by a factor of at least 1,000,000 trillion, possibly much more depending on exactly how long inflation lasted. This expansion occurred in approximately 10^32 to 10^34 seconds, a decimal point followed by 31 to 33 zeros, and then a 1. Human minds simply aren't evolved to grasp scales like this. Let's try a concrete analogy. Imagine a virus particle so small you'd need a powerful electron microscope just to detect it, about 100 nanometers across. Inflate it through 80 doublings using the same expansion factor, and it becomes larger than the entire observable universe, which spans 93 billion light-years. That's the scale of expansion we're discussing. What makes inflation scientifically credible rather than wild speculation is that it solves real observed problems in cosmology. One is called the flatness problem. Space can curve in different ways mathematically. It can curve positively like the surface of a sphere, negatively like a saddle, or be perfectly flat like an infinite plane. Measurements from the Planck satellite and other sources show our universe is extraordinarily flat to within 0.4% margin of error. So flat that if you fired a laser beam across the entire observable cosmos, it would travel in an almost perfectly straight line for 93 billion light-years. The standard Big Bang model couldn't explain this. Tiny deviations from perfect flatness in the early universe should have grown enormously over billions of years through gravitational effects. We should live in a universe that curves dramatically. We don't. Inflation solves this elegantly by stretching space so much that any initial curvature got smoothed out completely. It's like inflating a balloon. The surface becomes flatter and flatter as it expands, even though it started highly curved. Another problem is the horizon problem, which we touched on earlier. Light has only had 13.8 billion years to travel since the Big Bang began. That means regions of space separated by more than about 28 billion light-years, accounting for expansion, have never been in causal contact. They've never exchanged information, yet when we measure their properties, temperature, density, expansion rate, physical constants, they're identical to extraordinary precision. How did they coordinate? Inflation answers this definitively. Those distant regions were once close together, in contact, able to reach thermal equilibrium and the same physical state. Then inflation separated them faster than light could reconnect them. The coordination happened before inflation, and the uniformity we observe today is the preserved memory of that earlier contact. The evidence supporting these 60-80+ doublings keeps growing stronger each year. Satellite missions have mapped the cosmic microwave background with incredible detail, measuring billions of data points across the sky. The pattern of fluctuations matches inflation predictions to extraordinary precision. Alternative theories that don't invoke inflation have been proposed: ekpyrotic scenarios, bouncing cosmologies, varying speed of light theories, but they fail to reproduce the full range of what we observe with the same accuracy and simplicity. Scientists calculate that inflation must have lasted long enough for at least 60 doublings to occur, with 80+ doublings more likely based on solving the flatness and horizon problems. The exact number remains uncertain because we can only observe the effects within our observable universe, which represents just the tiny patch we can see. Inflation might have stretched space far beyond what we can detect, creating regions forever hidden beyond our cosmic horizon, causally disconnected from us by the finite speed of light and the expansion of space. This means the universe you can see, every galaxy observed by the Hubble Space Telescope, every star cluster, every bit of light, represents just one minuscule patch of a vastly larger reality. And it all came from a cold, nearly empty vacuum expanding faster than physics should seemingly allow, powered by an energy field we still don't fully understand. Part 12. The ekpyrotic universe. Collision in higher dimensions. What if our universe wasn't born from vacuum fluctuations or quantum tunneling, but from two massive structures smashing together in a higher dimension? What if everything we see came from a cosmic collision? This is the ekpyrotic model, named after the ancient Stoic concept of ekpyrosis, a cyclical conflagration and rebirth of the cosmos. And it's built on serious, sophisticated mathematics. The theory emerges from string theory, a framework that describes fundamental particles not as point-like objects but as tiny vibrating strings about 10 and 35 meters long, the Planck length. String theory, developed primarily in the 1970s through 1990s by physicists including Edward Witten, Leonard Susskind and many others, requires extra dimensions beyond the three of space and one of time we experience directly. The mathematics doesn't work without them. In the most studied version, called M-theory, there are 11 dimensions total, the 4 we know plus 7 additional spatial dimensions. These extra dimensions could be curled up incredibly small, or they could be large but hidden from our direct perception through the way forces and matter are confined. In some versions of string theory, our entire universe exists on a three-dimensional membrane called a brane for short, floating in higher dimensional space. Think of a sheet of paper existing in a three-dimensional room. We're trapped on the sheet, unable to move perpendicular to it into the extra dimensions, while the room contains spaces we can't access. The ekpyrotic model, proposed in 2001 by physicists including Paul Steinhardt of Princeton and Neil Turok of the Perimeter Institute, suggests there are two such branes parallel to each other in the higher dimensional space, separated by a tiny distance in the extra dimension. An attractive force, perhaps gravitational, perhaps from string tension, pulls these branes together over vast spans of time. They approach slowly at first over perhaps trillions of years, building up potential energy. Then they collide with enormous force. The collision releases tremendous energy into both branes. From our perspective, trapped on one brane and unable to perceive the extra dimension, this would look exactly like the Big Bang. Matter and radiation flood our three-dimensional space. The universe heats up rapidly to extreme temperatures, space expands, the cosmos cools and evolves into everything we observe today. But it wasn't a beginning from nothing, it was a crash between pre-existing structures in higher dimensional space. This theory solves several problems that plague standard inflationary models. First, it explains why the universe is flat and uniform without requiring exponentially fast expansion. The slow approach of the branes over enormous time periods smooths out any irregularities and inhomogeneities before impact. By the time they collide, both branes are extraordinarily uniform, producing a uniform Big Bang. Second, it explains the pattern of fluctuations in the cosmic microwave background as vibrations created by the collision itself. Just as striking a bell creates sound waves with specific frequencies, the brane collision creates space-time ripples with predictable properties. Third, it avoids the multiverse problem that plagues eternal inflation. If inflation lasts long enough, which it does in most models, it produces an infinite number of pocket universes with random properties. This makes the theory extremely difficult to test because any observation can be explained by saying we just happen to live in this particular pocket. The eukaryotic model doesn't have this issue. One collision creates one universe with predictable, calculable properties that can be compared directly to observations. However, the eukaryotic scenario faces significant challenges and criticisms. Nobody fully understands what happens during a brain collision at the mathematical level. String theory and M-theory aren't developed enough yet to precisely calculate the outcome with certainty. The equations become extremely complex, involving quantum effects, strong gravitational fields, and higher dimensional geometry all at once. Some critics argue the collision might destroy the smoothness that the model depends on, creating irregularities rather than uniformity. Others point out that getting the right spectrum of density fluctuations, matching what we observe in the cosmic microwave background, requires careful fine-tuning of the collision parameters, like the brane separation and approach speed. Despite these difficulties, the eukaryotic model remains scientifically viable and actively researched. It makes testable predictions that differ from inflation in measurable ways. For example, it predicts that primordial gravitational waves from the collision would be too weak to detect in the cosmic microwave background polarization. Standard inflation predicts they might be strong enough to detect with current or near-future technology. If future experiments detect strong B-mode polarization from primordial gravitational waves, it would favor inflation over chi process. If searches continue to find nothing despite increasing sensitivity, it would favor chi-protic models. The chi-protic model also connects to something deeper and more profound, the idea that our Big Bang wasn't unique or special. If brains can collide once, they can collide multiple times. The collision could bounce the brains apart like elastic balls. They'd separate, drift through the higher dimension under the influence of various forces, then get pulled back together by the attractive force. Another collision, another Big Bang. This leads naturally to a cyclic cosmology, where the universe goes through endless cycles of collision and separation. Each cycle creates a cosmos that lives for trillions of years. Each cycle eventually ends when the brains separate. Then the process repeats indefinitely into both the future and the past. From our perspective, trapped on one brain, it would look like the universe expands for trillions of years until it becomes cold and empty, then somehow transitions into a new hot, dense phase, a new Big Bang. But the transition happens through a collision in a higher dimension we can't perceive directly. The implications are staggering for our understanding of cosmic origins. The singularity at the beginning of time, the point of infinite density that has haunted physics for decades, might not exist at all. It might be an artifact of looking at the collision from within our limited three-dimensional perspective. From the higher dimensional perspective, there's no singularity, no beginning, no moment of creation. There are just brains moving through higher dimensional space, occasionally colliding and creating what appear to us as Big Bangs. This is the universe as an eternal process, rather than a created thing. Part 13, The Big Bounce, Quantum Gravity to the Rescue. The singularity problem has been a thorn in physics' side since Einstein's equations were first applied to cosmology. The mathematical prediction of infinite density and infinite curvature at the beginning of time seems obviously unphysical. Nature doesn't do infinities in reality, only in the approximations we use when our theories break down. The Big Bounce theory offers an elegant solution grounded in quantum gravity. Instead of the universe beginning at a singularity of infinite density, it transitions smoothly from a contracting phase into our current expanding phase. The bounce happens at a finite though extremely high density, no infinities, no breakdown of physics. This idea isn't wishful thinking. It's grounded in loop quantum gravity, one of the leading approaches to combining quantum mechanics and general relativity into a unified theory. Loop quantum gravity, developed primarily by Carlo Rovelli, Lee Smolin, Abhay Ashtekar and others starting in the 1980s, treats spacetime itself as quantized, made of discrete units at the smallest scales. In this framework, space isn't a smooth continuum, but a network of tiny quantum loops connected like microscopic chainmail. Each loop occupies a minimal area of about 10^70 square meters and a minimal volume of about 10^105 cubic meters, the Planck area and Planck volume. At normal scales, this discrete structure averages out, and space appears smooth, just like a television screen looks continuous from a distance, but is actually made of discrete pixels when you examine it closely. The crucial insight comes when you apply these ideas to the Big Bang singularity. In classical general relativity, matter collapsing or the universe contracting can reach infinite density. But loop quantum gravity says space has a minimum volume determined by quantum effects. You fundamentally cannot compress something smaller than the Planck volume, which is about 4·10⁵ cubic meters. It's not a technological limitation, it's a feature of quantum geometry. When a collapsing universe reaches this maximum density, approximately 5·10⁵96 kilograms per cubic meter, which is about 10⁵101 times denser than an atomic nucleus, quantum repulsion kicks in. The mathematics shows that gravity effectively reverses at these densities, becoming repulsive instead of attractive. The collapse halts and reverses into an expansion. The singularity gets replaced by a bounce, a smooth quantum bridge connecting contraction to expansion. This isn't hand-waving or speculation. Scientists have performed detailed calculations using the equations of loop quantum gravity. They've simulated how a universe evolves through the bounce using powerful computers. The results, published in numerous peer-reviewed papers since the early 2000s, show that cosmological perturbations, the tiny fluctuations that seed galaxies and large-scale structure, can propagate through the bounce without being destroyed. Information survives the transition from the pre-bounce universe to the post-bounce universe. Abhay Ashtekar and his collaborators at Pennsylvania State University have led much of this research over the past 2 decades. Their work shows that a pre-bounce universe undergoing slow contraction would generate a nearly scale-invariant spectrum of perturbations, matching exactly what we observe in the cosmic microwave background. The bounce doesn't erase this structure, it preserves it, allowing patterns from the contracting phase to seed structure in the expanding phase. This creates a testable prediction that distinguishes the bounce from standard inflation. Loop quantum gravity bounces should produce specific signatures in gravitational waves that differ subtly from what inflation predicts. The spectrum of gravitational waves should have a different shape at certain frequencies. As gravitational wave detectors become more sensitive over the coming decades, with facilities like LIGO, Virgo, CAGRA, and the planned LISA space mission, they might be able to distinguish between these scenarios. There's also a profound philosophical shift here that goes beyond the mathematics. Loop quantum gravity doesn't require invoking anything beyond known physics, extended to quantum scales. It doesn't need extra dimensions, it doesn't need colliding brains, it doesn't need exotic forms of matter or energy. It simply takes quantum mechanics seriously at all scales, including space-time itself. The singularity that terrified and confused physicists for nearly a century disappears. It was never real, just an artifact of using classical equations where they don't apply, like using Newtonian physics to describe subatomic particles. Once you properly account for quantum effects which dominate at Planck scales, the universe has no beginning or end in the traditional sense. It's a continuous process with phases of expansion and contraction connected by quantum bounce events. This resolves the ancient paradox of creation. You don't need to explain how something came from absolute nothing, because there was never absolute nothing in the first place. There was always quantum spacetime structure, eternally transforming between different states, sometimes expanding, sometimes contracting, sometimes bouncing, but always existing, always evolving according to the laws of quantum geometry. But what triggered our particular expansion phase? What determined the conditions in the pre-bounce universe? And does this process repeat infinitely? These questions lead us to cyclic cosmology. Part 14, Eternal Cycles of Creation. Imagine a cosmos that never began and never ends. A universe caught in an eternal rhythm. Expansion, contraction, bounce, expansion again. Each cycle lasting trillions of years. Each cycle creating conditions for stars, planets, and possibly life. Each cycle different, yet connected to those before and after. This is cyclic cosmology, one of the most ambitious and philosophically profound ideas in modern physics. The concept isn't new. Ancient Stoic philosophers in Greece and Rome, including Chrysippus and Marcus Aurelius, proposed an eternal cycle of cosmic creation and destruction they called a kaprosis. Hindu cosmology describes similar cycles over vast timescales called kalpas, each lasting 4.32 billion years in their traditional calculation. But modern physics puts these ancient intuitions on firm mathematical and observational ground. In the cyclic model developed by Paul Steinhardt and Neil Turok in the early 2000s, based on the acaprotic brain collision scenario we discussed earlier, dark energy plays a crucial role in making cycles eternal. Remember, dark energy is the mysterious component causing our universe's expansion to accelerate. It makes up about 68% of the total energy of the cosmos. In the far future, dark energy will push galaxies so far apart that the universe becomes essentially empty from any given perspective. Matter gets diluted to negligible density. Stars burn out their nuclear fuel. The last red dwarfs will fade in about 10 trillion years. Black holes evaporate through Hawking radiation over incomprehensible timescales. The supermassive black hole at our galaxy's center won't evaporate until about 10⁻100 years from now. Eventually, perhaps 10⁻150 years in the future, the universe becomes a cold, dark, nearly empty expanse with only random photons and exotic particles occasionally flickering through the void. But in the ekpyrotic cyclic model, the dark energy doesn't disappear. It continues to exist, permeating space, and the same attractive force between brains that caused our Big Bang collision continues to operate through the higher dimension, over trillions upon trillions of years, timescales that make the current age of the universe seem like an eye blink. This force pulls the brains together again through the higher dimensional space. Another collision occurs, another Big Bang erupts, a new universe begins, fresh and hot, ready to evolve its own galaxies, stars, and potentially life over the next trillion years. Crucially, each cycle doesn't produce identical conditions. The universe grows larger with each iteration. The scale factor, a measure of cosmic size, increases from cycle to cycle, allowing the universe to hold more space and more potential structure. Entropy builds up as required by the second law of thermodynamics, but it gets diluted by the ever-increasing expansion. The total entropy increases, but the entropy density decreases because volume grows faster than entropy accumulates. This solves the entropy problem that killed earlier cyclic models. In the 1930s, physicist Richard Tolman at Caltech explored cyclic universes using Einstein's equations. He showed that a naively cyclic universe would accumulate entropy until thermal equilibrium was reached, at which point no more bounces could occur. Each cycle would be longer and less energetic than the last, eventually grinding to a halt. The Steinhardt-Turok model avoids this entropy death by incorporating dark energy and allowing the universe to expand net over many cycles. Each cycle leaves the universe larger than before, providing infinite room for entropy to spread out without reaching equilibrium. Another cyclic proposal comes from Roger Penrose, the Nobel laureate mathematician and physicist at Oxford. His conformal cyclic cosmology, CCC, proposed in 2005, takes a completely different approach. Penrose suggests the universe expands forever until all matter eventually decays into radiation, photons, and other massless particles. This might take 10,500 years or more, but in Penrose's framework, it's inevitable. At that point, nothing remains with rest mass. Everything moves at the speed of light. And here's the key insight. When nothing has mass, the concepts of time and distance become meaningless mathematically. Photons don't experience time from their own perspective, due to relativistic time dilation. If you could ride on a photon, the entire history of the universe from beginning to end would pass in what seems like zero time. Penrose argues this massless state can be mathematically mapped onto a new Big Bang. The infinite future of one universe, an eternity from our perspective, becomes the hot, dense beginning of the next. Time becomes circular, or perhaps spiral. It's conformal because the geometry is preserved under this transformation even though scales change. Angles and shapes remain the same, but sizes can be arbitrarily scaled. These models remain speculative and face significant challenges. They're testable in principle, but difficult to test in practice. They predict specific patterns in the cosmic microwave background. Some versions of CCC predict we might see circular patterns, concentric rings in the temperature map, from gravitational waves generated by colliding black holes in the previous cycle. These rings would be imprinted in the CMB radiation. Penrose and his collaborators claimed to find such patterns in WMAP data in 2010, but the statistical significance has been heavily debated. Most cosmologists remain skeptical, arguing the patterns could easily arise by chance from random fluctuations. Other searches have been conducted using Planck data, also with controversial and inconclusive results. So far, no definitive signals of a previous cycle have been confirmed, but the search continues as data quality improves and analysis techniques become more sophisticated. Cyclic cosmology offers profound philosophical appeal, regardless of which specific model proves correct. It removes the awkward question of why the universe exists at all. It always has existed, and always will, changing form, transforming through cycles, but never truly beginning or ending in an absolute sense. Existence becomes the fundamental ground state, while specific configurations like our current expanding universe with its galaxies and stars become temporary phases in an eternal process. But cyclic models also raise fascinating new questions. If cycles repeat forever into the past, have there been infinite cycles? Mathematics allows it, but does physics? Does the universe have memory of earlier cycles? Do physical constants remain the same, or do they evolve from cycle to cycle? And if constants change, could each cycle operate under different physical laws entirely? This leads to one of the most speculative yet scientifically grounded ideas in all of cosmology. Part 15. Variable physical laws across cycles. Here's a possibility that sounds like pure science fiction, but emerges from serious theoretical physics. Each cycle of the universe might operate under different physical laws. The constants that govern particle masses, force strengths, and cosmic behavior could shift from one cycle to the next. Why would this happen? In many theoretical frameworks developed over the past 30 years, the values of physical constants aren't set by fundamental principles etched into the fabric of reality. They're environmental, determined by how quantum fields settle into their lowest energy states during cosmic evolution. It's analogous to water freezing. The exact pattern of ice crystals depends on random fluctuations during the freezing process, temperature variations, impurities, vibrations. Each time water freezes, you get a slightly different crystal structure, even though the underlying physics is identical. During a bounce or brane collision, the extreme energies involved, densities of 1096 kg and temperatures of 1032 Kelvin, could reset these quantum fields completely. As the new universe expands and cools, the fields would settle into new configurations based on quantum randomness, different constants, different physics, a cosmos that looks and behaves differently from ours in fundamental ways. This has staggering implications for understanding cosmic history. In most cycles, the constants might not allow complex structures to form at all. If the strong nuclear force were just 2% weaker, atomic nuclei wouldn't bind together. No atoms heavier than hydrogen could exist. If it were 2% stronger, all hydrogen would have fused into helium shortly after the Big Bang, leaving no fuel for long-lived stars. If the electromagnetic force were slightly different, chemistry wouldn't work. If gravity were stronger relative to other forces, stars would burn out in millions of years instead of billions, giving no time for life to evolve. Most random combinations of constants would produce sterile, simple, short-lived universes, perhaps just expanding clouds of particles that never clump into anything interesting, perhaps universes that collapse immediately, perhaps universes where matter cannot form at all. But occasionally, purely by random chance over infinite cycles, the constants would align just right. Atoms could form, gravity could pull matter into stars and galaxies, nuclear fusion could produce the periodic table of elements, chemistry could create complexity, life might emerge. We necessarily find ourselves in one of those rare successful cycles because we couldn't exist in any other kind. This is a version of the anthropic principle applied to cyclic cosmology. The anthropic principle, controversial but unavoidable in many cosmological frameworks, observes that the universe must be compatible with the conscious life that observes it. We shouldn't be surprised that our universe has life-permitting constants, because in a universe without them, nobody would exist to notice. In a cyclic multiverse where each cycle has different physics, the anthropic principle explains our particular set of constants without requiring divine fine-tuning or incredible coincidence. All possible values occur somewhere in the infinite cyclic sequence. We observe life-permitting values because only those cycles contain observers. Some physicists find this explanation deeply unsatisfying. It replaces one mystery, why our constants have these specific values, with another assumption, that all possible values occur somewhere. You haven't really explained anything, they argue. You've just moved the mystery one level deeper without adding predictive power. Others embrace anthropic reasoning as the only logical explanation. If the cyclic model is correct and constants vary between cycles, then anthropic selection becomes necessary and testable. We can make statistical predictions based on anthropic reasoning. We should find ourselves in a typical life-permitting cycle, not a maximally life-permitting one. Our universe should be close to the boundary where complex structures barely form, right on the edge of possibility. Too far from the boundary would be statistically unlikely. If you're randomly selecting from all life-permitting configurations, you're most likely to land near the minimum requirements, not far beyond them. Some evidence tentatively supports this. The cosmological constant in our universe, the energy density of the vacuum, sits uncomfortably close to the maximum value that would allow galaxies to form through gravitational collapse. Current measurements put it at about 6×10 joules per cubic meter. If it were about 10 times larger, still incredibly tiny in absolute terms, cosmic expansion would have accelerated so fast that matter could never clump together. No galaxies, no stars, no planets, no us. If it were much smaller, we'd need to explain why it's not exactly zero, which would be the natural value from symmetry arguments. We seem to be near a boundary, which cyclic anthropic reasoning predicts.
We're in a cycle where structure barely forms, rather than one where structure formation is easy and abundant. Steven Weinberg, Nobel laureate physicist, made a famous anthropic prediction about the cosmological constant in 1987, before dark energy was discovered. He calculated that the constant couldn't be more than about 100 times larger than the critical density needed to produce galaxies, or we wouldn't exist. When dark energy was discovered in 1998, its value fell within Weinberg's anthropically predicted range, a stunning success for anthropic reasoning that convinced many skeptics to take it seriously. Testing whether constants actually varied in previous cycles is nearly impossible directly. The bounce or collision erases most information about what came before, quantum effects wash out details, but some theories suggest subtle imprints might survive. Topological defects, certain kinds of knots or twists in spacetime, could potentially persist through a bounce. If detected, they might carry information encoded in their structure about the previous cycle's physics. More realistically, we can test whether the theoretical frameworks allowing variable constants make sense and are consistent with what we observe. String theory, for example, predicts a vast landscape of possible vacuum states. The number of distinct configurations is estimated at 10^500 or more, far more than the number of atoms in the observable universe. Each configuration represents a different way the extra dimensions can be shaped and the quantum fields can be arranged. Each produces different effective laws of physics in our three large dimensions. Exploring which of these states are accessible, how transitions between them might occur during extreme events like bounces or brain collisions, and what patterns we should observe is active research. The big picture emerging from cyclic cosmology with variable physics is simultaneously humbling and grand. Our universe isn't special, it's not fine-tuned by design, it's one outcome of an eternal process that generates cosmos after cosmos after cosmos. Most of them are failures from the perspective of complexity. Some are interesting, a few give rise to observers who can ask these profound questions. We're left with a vision of reality far stranger and richer than the simple something-from-nothing narrative that dominated popular science for decades. There might be no ultimate beginning, no final end, no single set of physical laws that apply everywhere and everywhen. Just an infinite churning of possibilities with brief windows, perhaps lasting hundreds of billions of years, where complexity flourishes before dissipating back into simplicity, then re-emerging in a new form with different rules. The universe in this view is not a creation event, it's an eternal transformation, constantly reinventing itself.
Part 16. Quantum gravity and the singularity problem. General relativity and quantum mechanics are the two pillars of modern physics, both confirmed to extraordinary precision, but fundamentally incompatible with each other. General relativity, Einstein's theory of gravity published in 1916, describes how massive objects curve spacetime. It predicts black holes, gravitational waves, and the expansion of the universe. Every prediction has been confirmed, from the orbit of Mercury to the direct detection of gravitational waves by LIGO in 2015. Quantum mechanics, developed primarily in the 1920s by Heisenberg, Schrödinger, and Dirac, governs atoms, particles, and the microscopic world. It predicts atomic spectra, chemical bonds, and semiconductor behavior. Modern technology, from computers to MRI machines, depends on its accuracy. Both theories work brilliantly in their domains, but they contradict each other at extreme scales where both quantum effects and gravitational effects become strong simultaneously. Scales like the Big Bang singularity or the center of black holes. You desperately need a theory of quantum gravity, a framework that incorporates both sets of principles consistently, without contradiction. Nobody has one yet that's complete, tested, and universally accepted by the physics community. String theory offers one approach. It replaces point particles with vibrating strings, which smooths out the singularities. The mathematics is elegant. The theory potentially describes all forces and particles within one unified framework, but it requires extra dimensions we can't see. It has about 10^500 possible vacuum states with no clear way to select which one describes our universe, and it makes very few testable predictions at energies accessible to current experiments. Loop quantum gravity takes a completely different route. It quantizes spacetime directly, treating space as a network of discrete quantum loops rather than a smooth continuum. This automatically avoids singularities because space has minimum quanta. It explains how space emerges from quantum building blocks, but it struggles to incorporate matter fields and forces beyond gravity. Connecting it properly to the standard model of particle physics remains challenging after decades of effort. Other approaches exist as well. Causal dynamical triangulations build spacetime from simple geometric pieces and evolve it through quantum rules. Asymptotic safety suggests gravity might remain mathematically well-behaved at arbitrarily high energies through a special property called a non-trivial fixed point. Emergent gravity theories propose that spacetime isn't fundamental at all but emerges from more basic quantum information, similar to how temperature emerges from molecular motion. Each approach has strengths and significant weaknesses. Each makes different predictions about Planck scale physics, and frustratingly, directly testing these predictions is nearly impossible with current or foreseeable technology. The energies required are too high by factors of trillions. The scales are too small by factors of trillions. We can't build particle accelerators powerful enough or microscopes precise enough to directly probe Planck scale physics. But cosmology provides an indirect testing ground that might be our only hope. The early universe naturally probed Planck-scale physics. For a brief moment, around 10^43 seconds after the Big Bang, or the bounce, quantum gravity effects dominated everything. The universe was a quantum gravitational system. If we can decode the messages written in observational data, the cosmic microwave background, the spectrum of gravitational waves, the distribution of large-scale structure, we might be able to distinguish between competing quantum gravity theories. This is why understanding what happened before or during the Big Bang matters so profoundly for fundamental physics. It's not just philosophical curiosity. The origin of the universe is the one natural laboratory where quantum gravity was fully operational, running at maximum strength, leaving fingerprints we can potentially read with sufficiently sensitive instruments and clever analysis. The battle between quantum mechanics and general relativity will eventually be resolved. When it is, whether in 10 years or 100, we'll have a complete picture of how spacetime and matter work at all scales. And with that understanding, we'll finally know what nothing really means in the deepest possible sense. What is the true quantum vacuum? What is the fundamental ground state of reality? Can it ever be truly empty? Or does the structure of quantum geometry forbid absolute nothingness? These aren't just abstract questions. They determine whether the universe could have had an absolute beginning, or whether existence is eternal in some form. Part 17. String theory and hidden dimensions. We experience 3 dimensions of space in our daily lives: left, right, forward, backward, and up, down. Add time as a 4th dimension, and you get the 4-dimensional spacetime of Einstein's relativity. String theory says there are at least 7 more dimensions beyond these, giving a total of 11 dimensions in the most complete version called M theory. Why haven't we noticed them? The theory proposes they're compactified, curled up so small that we can't perceive them directly, even with our most powerful microscopes and particle accelerators. Imagine an ant walking on a telephone wire stretching between 2 poles. From far away, the wire looks one-dimensional. The ant can only move forward or backward along its length. But zoom in close, and you discover the wire has thickness. The ant could walk around its circumference, exploring a 2nd dimension we initially missed because it's curled up small. The extra dimensions in string theory work similarly. They exist at every single point in our familiar 3-dimensional space, but they're rolled up at scales far tinier than atoms, typically around the Planck length of 10^35 meters. Particles aren't truly point-like in this framework. They're tiny vibrating strings about 10^35 meters long, so small that even at the highest energies achieved at the Large Hadron Collider, they appear as points because we can't resolve structure at that scale. Different vibration patterns of these strings appear to us as different types of particles. An electron is one vibration mode, a quark is another mode. Photons, neutrinos, W and Z bosons, everything in the standard model of particle physics emerges from strings vibrating through these higher dimensional spaces. Even gravity itself emerges naturally from string theory. One particular vibration pattern has exactly the right properties to be the graviton, the hypothetical quantum particle that carries gravitational force. This is string theory's greatest achievement. It's the only known framework that successfully incorporates quantum gravity in a mathematically consistent way. Part 18. Eternal inflation and the multiverse. Inflation was supposed to be a one-time event, a brief period of exponential expansion lasting perhaps 10^32 seconds that set up the conditions for our Big Bang, then ended cleanly. But the mathematics suggests something far stranger and more profound. Once inflation starts in any region of space, it might never completely stop everywhere. The process becomes eternal, spawning an infinite number of universes. Here's why this happens according to the equations. Inflation is driven by a quantum field called the inflation field, represented by the Greek letter phi, phev. When this field has a high energy value sitting at the top of what physicists call its potential energy curve, space expands exponentially fast. As the field slowly rolls down this potential curve toward lower energy, like a ball rolling down a hill, inflation continues but begins to slow. When the field finally reaches the bottom, its minimum energy state, inflation stops. The field's potential energy converts to particles and radiation. That's the Big Bang transition. In a classical universe with no quantum effects, this would happen uniformly everywhere. The field would roll down smoothly, inflation would end. The Big Bang would occur simultaneously throughout space, but we don't live in a classical universe. Quantum mechanics rules at fundamental scales. The inflation field experiences quantum fluctuations just like everything else, random jitters in its value caused by the Heisenberg uncertainty principle. In most regions of space, these fluctuations are small, and the field successfully rolls down to its minimum. Inflation ends. Those regions produce hot Big Bang conditions. But in some regions, purely by chance, quantum fluctuations push the field back up to higher energy before it can finish rolling down. In those regions, inflation doesn't stop. It continues, driving exponential expansion in that patch of space. Meanwhile, within those still inflating regions, new random fluctuations constantly occur. Most allow the field to roll down and end inflation, but some push it back up again, perpetuating inflation in subregions. This creates a fractal structure. Our observable universe is one finite pocket where inflation ended successfully about 13.8 billion years ago, but beyond our cosmic horizon, beyond the roughly 46 billion light-year radius we can observe, other regions are still inflating right now, and within those currently inflating regions, new pockets constantly form where inflation stops, creating new Big Bang universes. Each pocket expands, cools, potentially develops galaxies, stars, and life. Meanwhile, the background space between pockets continues inflating faster than light, forever separating them. The process never ends globally, though it ends locally in individual pocket universes like ours. Inflation continues eternally in the background, spawning an infinite number of pocket universes over infinite time. Alan Guth at MIT and Andre Linde at Stanford developed this eternal inflation framework in the 1980s. It's not a speculative add-on to inflation, it's a natural, almost inevitable consequence of combining inflation theory with quantum mechanics. The implications are staggering and philosophically profound. There's not one universe, there's a vast, possibly infinite multiverse. Our Big Bang is just one bubble in an endless foam of universes, each with its own history. Each bubble might have different properties determined by how quantum fields settled into their lowest energy states during that bubble's formation. The quantum fluctuations that create new pockets could also affect the values of physical constants, producing pocket universes with different laws of physics. Some pockets might have a strong nuclear force 10% different from ours. Others might have different electron masses, different gravitational constants, different numbers of particle types. Most combinations would produce sterile, lifeless universes, but some, like ours, would permit complex structure and possibly life. This naturally explains why our universe has life-permitting constants without requiring fine-tuning or design. There are infinite universes with all possible constants across the multiverse. We necessarily find ourselves in one compatible with our existence because we couldn't evolve anywhere else. It's anthropic selection on a cosmic scale. But eternal inflation also creates severe scientific and philosophical challenges. If every possible observation occurs somewhere in an infinite multiverse, how can we make predictions? Traditional science requires theories that predict what we should observe versus what we shouldn't. The multiverse seems to allow everything, predicting nothing specifically about our observations. This has led to intense debates among physicists. Some argue the multiverse makes science impossible because it lacks predictive power. Others counter that we can still make probabilistic predictions by counting which types of observers are most common across the multiverse. A controversial approach called the measure problem. Eternal inflation also has implications for the past. The Borda-Guth-Vilenkin theorem, proved in 2003 by Arvind Borda, Alan Guth, and Alexander Vilenkin, shows that any region of space expanding on average like eternal inflation must have a boundary in the past. Inflation can't be eternal into the past. It must have started somehow from some initial condition at some point in the finite past. This brings us back to the origin question: what triggered inflation in the first place? Where did the inflation field and its potential energy come from? Possible answers include a metastable false vacuum that decayed quantum mechanically, a prior contracting phase that bounced, a brane collision in higher dimensions, or quantum tunneling from literally nothing using the Wheeler-DeWitt equation. The theorem doesn't tell us which answer is correct. It only proves mathematically that there was a beginning to the inflationary process, even if inflation continues eternally into the future. Some physicists find eternal inflation disturbing precisely because it leads to this bizarre multiverse where we can never observe or test most of reality. The other bubbles expand away faster than light. No signal can ever reach us from them. They're causally disconnected by the inflating space between bubbles. Others argue the multiverse remains scientific because it's a prediction of testable theories, not an assumption. We don't test the multiverse directly.
We test inflation and quantum mechanics. If both are correct and evidence strongly suggests they are, eternal inflation follows naturally as a mathematical consequence. The debate remains unresolved with passionate advocates on both sides, but observationally, we're confined to our bubble. We can study its properties exhaustively, mapping the cosmic microwave background, measuring expansion rates, cataloging dark energy, but all of this tells us only about our pocket universe. Whether infinite other pockets exist remains unknown empirically, but the mathematics of inflation plus quantum mechanics strongly suggests they do, with new ones forming constantly as eternal inflation churns onward. And if they do exist, then the question of what existed before the Big Bang becomes even stranger and more nuanced. Our Big Bang was not the beginning of inflation globally, it was the end of inflation locally in our region. Other regions never stopped inflating and continue expanding today. Still others ended inflation earlier or later, each with its own timeline and origin. There's no universal before the Big Bang that applies everywhere. Each pocket has its own timeline, its own origin point, its own history unfolding independently. The multiverse as a whole might be timeless, pockets beginning and ending at all possible moments, embedded in an eternal inflating background that has no beginning or end globally. This is the picture modern cosmology increasingly paints, not a simple creation story with one clear beginning. A complex, layered reality, where our universe is one small, perhaps infinitesimal piece of an infinite whole. Part 19. The illusion of the singularity. For decades, popular science and even many physics textbooks treated the Big Bang singularity as a physical reality, a point where the universe was infinitely dense, infinitely hot, infinitely curved in space-time, but physicists never actually believed it was real. A singularity in your equations signals the breakdown of your theory, not a description of reality. When mathematical equations give infinite answers, infinity for density, infinity for temperature, infinity for curvature, they're telling you the framework no longer applies. You've pushed the model beyond its domain of validity into a regime where new physics takes over. General relativity predicts singularities in specific circumstances. Black holes have them at their centers according to the classical equations. The Big Bang has one at its beginning when you trace expansion backward in time. But general relativity is a classical theory from 1915. It doesn't include quantum mechanics, which wasn't fully developed until the 1920s. At small scales and high energies, quantum effects become absolutely crucial. Ignoring them guarantees your predictions will fail catastrophically. Think of it like predicting the behavior of water. Classical fluid mechanics works beautifully for describing rivers, waves, and water pipes, but at molecular scales where individual H2O molecules matter, you need quantum chemistry. Classical fluid equations give nonsensical results at atomic scales because they're simply the wrong tool for that regime. General relativity is the wrong tool at Planck scales. The Planck length is 1.616 10 by 135 meters. The Planck time is 5.391 10 by 134 seconds. The Planck energy is about 1.956 10 by 135 meters. The Planck time is 5.391 10 by 144 seconds. A singularity, which by definition requires compressing something into exactly zero volume with infinite density, becomes impossible. Quantum mechanics fundamentally won't allow it because of the uncertainty principle. Stephen Hawking and Roger Penrose proved famous theorems in the 1960s and 1970s, showing that general relativity predicts singularities under very general conditions. Their work was brilliant, groundbreaking, and earned Penrose the Nobel Prize in 2020. But it also highlighted exactly where general relativity fails. The singularity theorems tell us where we desperately need a better theory, one that includes quantum effects. Loop quantum gravity, as we discussed, replaces the singularity with a bounce at maximum density. String theory might replace it with a minimum size determined by string length scales. Other quantum gravity proposals have their own solutions to the singularity problem. The details differ significantly between approaches, but the conclusion is the same across all of them. The singularity isn't real. It was never a feature of nature. It was always an artifact of using incomplete equations. This means the Big Bang wasn't a moment when the universe sprang from absolute nothing into something. It was a transition from one quantum state to another state, a phase change in the quantum geometry of space-time. The pre-transition state might have been a contracting universe that bounced. It might have been an inflating false vacuum that decayed. It might have been a higher dimensional brane configuration. It might have been something else entirely that we haven't imagined yet. But it was something, not nothing. There was a pre-existing quantum structure obeying physical laws. The mathematical fiction of the singularity has misled generations of physicists, students, and the public. It made the origin of the universe seem more mysterious than it actually is, a creation from absolute nothingness requiring explanation beyond physics. Yes, we don't fully understand quantum gravity yet. The theory isn't complete. Yes, the precise details of what happened at Planck scales remain unclear and hotly debated, but we know with confidence that the universe didn't begin at an infinitely dense point because infinite density is unphysical. Nature doesn't do infinities. Math does infinities when your equations break down. This fundamentally shifts the question we should be asking. We're not trying to explain how something came from absolute philosophical nothing, a state with no matter, no energy, no space, no time, no laws, no mathematics. We're trying to explain what the pre-Big Bang quantum state was, why it existed, and why it transitioned into our current expanding universe. That's still a profound question, but it's a tractable scientific question that physics can potentially answer, rather than a metaphysical mystery requiring explanations beyond the natural world. Part 20. Reconciling quantum mechanics and gravity. Quantum mechanics and general relativity are both experimentally confirmed to extraordinary precision, yet they fundamentally contradict each other when you try to combine them. This isn't a minor technical problem that physicists can patch up with clever mathematics. It's a fundamental clash of principles that has resisted solution for nearly a century. Quantum mechanics predicts the behavior of atoms, lasers, transistors, and computer chips with perfect accuracy. When engineers design a semiconductor device, they use quantum mechanics to calculate how electrons will behave. The calculations work flawlessly every time. Modern technology exists because quantum mechanics is correct to at least 12 decimal places of precision. General relativity predicts the orbits of planets with incredible accuracy. It predicted gravitational lensing in 1915, confirmed observationally in 1919. It predicted gravitational time dilation, confirmed with atomic clocks on airplanes in the 1970s. It predicted gravitational waves detected directly by LIGO in 2015 from colliding black holes 1.3 billion light-years away. Both theories work perfectly in their respective domains, but they make contradictory statements about reality at the deepest level. In quantum mechanics, you can measure a system's energy with arbitrary precision if you're willing to wait long enough. Time is a background parameter that flows uniformly, the same for all observers. It's absolute. In general relativity, time is part of the dynamic, flexible fabric of spacetime. Time runs at different rates depending on gravity and motion. Clocks near massive objects tick slower than clocks in weak gravity. Clocks moving at high velocity tick slower than stationary clocks. There's no universal time that all observers agree on. Time is relative. In quantum mechanics, particles exist in superpositions. An electron can be in multiple places at once until you measure it. The wave function describes a cloud of probabilities that collapse upon observation. In general relativity, spacetime has a definite classical geometry. You can't have spacetime in a superposition of different curvatures, or can you? General relativity doesn't even have the mathematical language to describe such a thing because it's a purely classical theory. These contradictions become critical at Planck scales where both quantum effects and gravitational effects are comparably strong. The Big Bang, black hole interiors, the moment of the bounce if it exists. You desperately need a theory of quantum gravity, a framework that incorporates both sets of principles consistently, without contradiction. Nobody has one yet that's complete, tested and universally accepted by the physics community. Each approach has strengths and significant weaknesses. Each makes different predictions about Planck-scale physics. And frustratingly, directly testing these predictions is nearly impossible with current or foreseeable technology. The energies required are too high by factors of trillions. The scales are too small by factors of trillions. We can't build particle accelerators powerful enough or microscopes precise enough to directly probe Planck-scale physics, but cosmology provides an indirect testing ground that might be our only hope. The early universe naturally probed Planck-scale physics. For a brief moment around 10⁻43 seconds after the Big Bang or the bounce, quantum gravity effects dominated everything. The universe was a quantum gravitational system. If we can decode the messages written in observational data, the cosmic microwave background, the spectrum of gravitational waves, the distribution of large-scale structure, the properties of black holes, we might be able to distinguish between competing quantum gravity theories. This is why understanding what happened before or during the Big Bang matters so profoundly for fundamental physics. It's not just philosophical curiosity or cosmological bookkeeping. The origin of the universe is the one natural laboratory where quantum gravity was fully operational, running at maximum strength, leaving fingerprints we can potentially read with sufficiently sensitive instruments and clever analysis. The battle between quantum mechanics and general relativity will eventually be resolved. When it is, whether in 10 years or 100, we'll have a complete picture of how space-time and matter work at all scales, from the smallest quantum fluctuations to the largest cosmic structures, and with that understanding, we'll finally know what nothing really means in the deepest possible sense. What is the true quantum vacuum? What is the fundamental ground state of reality? Can it ever be truly empty, or does the structure of quantum geometry forbid absolute nothingness? These aren't just abstract questions, they determine whether the universe could have had an absolute beginning, or whether existence is eternal in some form.
Part 8. Redefining the Big Bang. For decades, popular science treated the Big Bang as the moment when time, space, and matter sprang into existence from nothing, a cosmic creation event. That picture is outdated and misleading. Modern cosmology tells a fundamentally different story. The Big Bang was not a creation event. It was a transformation, specifically, the moment when the vacuum energy driving cosmic inflation converted into matter and radiation, flooding the universe with heat and particles. Think of it as a phase transition, similar to water turning into steam when heated, except far more violent and fundamental in nature. This understanding comes from carefully matching theoretical predictions to observational data. The cosmic microwave background radiation shows us what the universe looked like 380,000 years after the Big Bang. It's a nearly uniform glow of microwave radiation with tiny temperature variations, exactly what you'd expect if the universe was once much hotter and denser, then expanded and cooled over time. But here's the critical insight. If we trace that expansion backward in time using Einstein's equations of general relativity, we don't reach a true beginning. We reach a barrier, a point where temperatures approach 1032 Kelvin and densities become too extreme for our current theories to describe accurately. When the equations output infinities and break down, physicists call this a singularity, but it's more honest to call it the edge of our knowledge rather than a description of physical reality. Inflation changes this picture completely and fundamentally. Instead of time beginning at the singularity, time existed before during the inflationary phase. During inflation, the universe was cold, perhaps just a few degrees above absolute zero in many models, and nearly empty, filled only with vacuum energy from the inflation field. Clocks ticked, space expanded, cause and effect operated normally, at least in principle. Then inflation ended over a brief period. The energy that had been locked in the vacuum state during inflation needed to go somewhere. Physical laws require energy to be conserved. So as inflation stopped, the vacuum energy decayed and transformed into elementary particles, quarks, electrons, photons, neutrinos and others. These particles carried enormous kinetic energy, making them move at nearly the speed of light. Their collisions generated heat, tremendous amounts of heat spreading throughout space. Within the first second after this transition, the universe reached temperatures exceeding 10 billion degrees Celsius, hot enough to prevent atoms from forming, hot enough that only the most fundamental particles could exist without immediately breaking apart. This seething plasma of matter and energy is what we call the early Big Bang universe. But that heat wasn't present during inflation. Inflation was cold. The distinction is absolutely crucial for understanding cosmic origins. The Big Bang wasn't the start of everything. It was the warm-up phase that came after inflation ended. Scientists have traced this transition using both theoretical calculations and experimental data from particle physics. Particle accelerators like the Large Hadron Collider at CERN recreate the conditions of the early universe by smashing protons together at enormous energies up to 13 trillion electron volts. These experiments confirm how matter behaves at extreme temperatures and validate the equations cosmologists use to model the Big Bang's aftermath. The standard model of particle physics, tested to extraordinary precision, describes exactly what particles should exist and how they should interact in the first microseconds. The timeline now looks clear and well established. First, a cold quantum vacuum state. Second, inflation stretches it exponentially for about 10^32 seconds. Third, the inflationary energy transforms into heat and particles through reheating. That transformation is the Big Bang. Fourth comes the story you already know. Cooling, atom formation, starbirth, galaxy assembly over billions of years. So when did time actually begin? We're not certain yet. Possibly during inflation. Possibly before inflation in some pre-inflationary quantum state. The honest answer is that we've pushed the boundary of the unknown backward in time, but we haven't eliminated it entirely. And remarkably, there's evidence in the data that proves the universe existed before the traditional Big Bang. Part 9. Superhorizon fluctuations. There's a smoking gun hidden in astronomical measurements that proves the universe existed before the traditional Big Bang. It's buried in the cosmic microwave background data, and it's called superhorizon fluctuations. Here's what that technical term means. The cosmic horizon is the maximum distance light could have traveled since the Big Bang began 13.8 billion years ago. It sets a fundamental limit on how far information can spread through the universe. Regions beyond this horizon are causally disconnected. They've never been in contact with each other and never could be. The standard Big Bang model predicts that temperature variations in the cosmic microwave background should only exist on scales smaller than this horizon. Anything larger represents regions that never interacted, so they shouldn't show coordinated patterns or correlations. But that's not what we observe at all. The data shows temperature fluctuations and correlations on scales much larger than the cosmic horizon, vastly larger in some cases. These super-horizon features appear clearly in multiple independent measurements taken by the WMAP satellite 2001-2010, the Planck satellite 2009-2013, and various ground-based telescopes. The evidence is undeniable and has been confirmed by every major cosmological survey. How do you get coordinated patterns across regions that have never communicated? How do you get correlations between points in space that are causally disconnected and always have been under the standard Big Bang model? There's only one explanation that works. Those regions were in contact before the Big Bang occurred. During inflation, when the universe was tiny and cold, quantum fluctuations occurred across all of space. These fluctuations were microscopic variations in the inflaton field's energy density, completely random noise generated by quantum uncertainty. These quantum fluctuations became the seeds of all cosmic structure. Then inflation stretched those fluctuations to enormous sizes, far larger than any horizon scale. When the Big Bang happened and hot matter filled the universe, these already inflated quantum patterns were imprinted on space. They showed up as temperature variations in the primordial plasma. We observe those variations today as hot and cold spots in the cosmic microwave background radiation. The mathematics is precise and testable. Inflation predicts a specific pattern of correlations between temperature fluctuations and polarization in the cosmic microwave background. It predicts how the amplitude of fluctuations should vary with angular scale across the sky. It predicts the spectrum should be nearly but not perfectly scale invariant. Observations match these predictions with extraordinary precision. In 2003, the WMAP team published the first high-precision measurements showing the predicted correlation pattern, including features on superhorizon scales that the non-inflationary Big Bang model could not explain. The non-inflationary model predicted something entirely different, correlations only on subhorizon scales with different statistical properties. The data eliminated the old model and strongly confirmed inflation. 20 years later, with even more sophisticated instruments, the agreement has only improved. The Planck satellite mapped these fluctuations with such precision that scientists can now test inflation's predictions to fractions of a percent. Every test passes, every measurement confirms the theoretical expectations. The superhorizon correlations are exactly where inflation says they should be, with exactly the properties inflation predicts. This represents one of the strongest pieces of evidence in all of cosmology. The patterns we observe in the sky could not possibly exist if the Big Bang was the absolute beginning. They require a prior phase inflation, where the universe was smaller, colder, and governed by different physical processes. Think about what this means scientifically. We've moved beyond mere philosophical speculation about what came before the Big Bang. We have observational proof written in light that's been traveling for 13.8 billion years. The light from the ancient universe carries direct information about conditions that existed before the traditional Big Bang occurred. We can measure properties of that pre-bang state. We can test competing theories about it using real data. The universe keeps many secrets, but it also leaves clues for us to find and decipher. Part 10. The Cosmic Microwave Background, our window to the past. The cosmic microwave background is the oldest light in the universe, released approximately 380,000 years after the Big Bang. It's been traveling through space for over 13.8 billion years, covering a distance of about 46 billion light-years when accounting for cosmic expansion. When we capture this ancient radiation with telescopes and satellites, we're seeing a snapshot of the cosmos when it was incredibly young, hot and simple. But hidden within that snapshot is information from even earlier, from the inflationary epoch before the Big Bang, as we traditionally understand it. Here's how this works in precise detail. During inflation, the vacuum energy dominating the universe had quantum properties governed by the Heisenberg uncertainty principle. Like everything in quantum mechanics, it experienced random fluctuations, tiny variations in energy density occurring at every point in space. These weren't just microscopic ripples that stayed small. Inflation amplified them exponentially, stretching microscopic quantum jitters that started at scales of 10⁵35 meters into variations spanning millions, then billions of light-years. When inflation ended and the Big Bang transition occurred around 10⁵32 seconds, those variations became permanently imprinted on the distribution of matter and energy. Regions with slightly higher density, perhaps 1 part in 100,000 denser than average, would eventually form galaxy clusters under gravitational collapse over billions of years. Regions with slightly lower density would become cosmic voids, the empty spaces between galaxy filaments.
The structure of the entire observable universe, every galaxy supercluster, every cosmic Webb filament, every void traces directly back to quantum randomness during inflation, lasting just 10^32 seconds. The cosmic microwave background captures this information because the photons released 380,000 years after the Big Bang traveled through space that already had these density variations imprinted. Hotspots in the radiation come from regions that were slightly denser and therefore slightly warmer. Cold spots come from regions that were less dense and cooler. The pattern we observe today is literally a fossilized map of conditions created during inflation, preserved in light for 13.8 billion years. Scientists have measured this map with incredible detail using 3 major space missions. The Cosmic Background Explorer (COBE), launched in 1989, first detected these temperature variations, earning its principal investigators John Mather and George Smoot the Nobel Prize in Physics in 2006. The Wilkinson Microwave Anisotropy Probe (WAP), operating from 2001 to 2010, measured the temperature variations with much higher resolution, about 13 arc-minutes, or roughly 1/3 the width of the full moon. The Planck satellite, operating from 2009 to 2013, achieved even higher precision with resolution down to about 5 arc-minutes and temperature sensitivity of a few millionths of a degree. The temperature varies by only about 18 microkelvins, 18 millionths of a degree across the sky. The universe was remarkably uniform even at 380,000 years old, but within that near-perfect uniformity lies structure and information. Specific sizes of hot and cold regions appear more frequently than others, creating what cosmologists call the power spectrum, essentially a graph showing how much variation exists at different angular scales across the sky. Inflation makes precise, testable predictions about what this power spectrum should look like. The distribution of fluctuation sizes should follow a nearly scale-invariant pattern, meaning fluctuations of different sizes have almost the same amplitude with only slight deviations. The technical term is a spectral index close to 1, and observations measure it at approximately 0.965. This is exactly what inflation predicts. The match is so close, agreeing to within about 1%, that it's become one of the fundamental pillars of modern cosmology. But the cosmic microwave background reveals far more than just temperature variations. It also carries information about polarization, the orientation of the electromagnetic waves that make up this ancient light. Light becomes polarized when it scatters off charged particles like electrons. In the early universe, photons constantly scattered off the primordial plasma of electrons and protons. This scattering created polarization patterns that we can still measure today. There are 2 types of polarization patterns called E modes and B modes, named by analogy to electric and magnetic fields. E modes come from density variations, the same fluctuations that create hot and cold spots. B modes can come from 2 sources: gravitational lensing of E modes by intervening matter, and primordial gravitational waves from inflation. Detecting primordial B mode polarization from inflation remains one of cosmology's biggest goals. Inflation should produce gravitational waves as a byproduct of its exponential expansion, ripples in spacetime itself propagating outward from the inflationary era. These gravitational waves would have left a specific imprint on the polarization of the cosmic microwave background. Finding this signal would provide direct evidence of inflation's energy scale and offer a window into physics at temperatures far beyond what any particle accelerator can reach. Energies around 1016 GeV, about 1 trillion times higher than the Large Hadron Collider. Multiple experiments are searching for this signal right now. Ground-based telescopes like BICEP, background imaging of cosmic extragalactic polarization at the South Pole, the Atacama Cosmology Telescope in Chile, and the South Pole Telescope have been scanning the sky for years. In 2014, the BICEP-2 team announced a possible detection of primordial B modes, generating enormous excitement. However, further analysis showed the signal was contaminated by polarized dust emission from our own galaxy, a reminder of how difficult these measurements are. The search continues with improved instruments and better foreground subtraction techniques. Future satellite missions like Lightbird, planned launch 2032, and ground-based experiments like CMBS-4 aim to achieve the sensitivity needed for definitive detection or to rule out large classes of inflation models. Even without detecting gravitational waves yet, the temperature and polarization data we already have powerfully constrains inflation theories. Some models predict large gravitational wave signals. Those models are now ruled out by the lack of detection. Other models predict specific patterns in how fluctuations behave on different scales. Observations test those predictions and eliminate models that don't match. The cosmic microwave background has become a precision laboratory for studying the pre-Big Bang universe. Every improvement in measurement technology brings new insights and tighter constraints. The data keeps getting better, and our picture of inflation keeps getting clearer and more detailed. What this data reveals is a universe that existed in a state completely different from anything we experience today, a cold, nearly empty expanse dominated by vacuum energy, undergoing exponential expansion for an incomprehensibly brief moment, setting the stage for everything that would follow. Part 11. The nature of time itself. We assume time flows in one direction, from past to future. We remember yesterday but not tomorrow. Causes precede effects. The sequence of moments feels fundamental to reality, like space or matter. But what if time itself only began during inflation, or even later? What if the question what happened before the Big Bang is as meaningless as asking what's north of the North Pole? This isn't wild speculation or philosophy. It comes from taking Einstein's general relativity seriously at the deepest level. Einstein's theory, published in complete form in 1916, showed that time and space are linked as spacetime, a four-dimensional fabric that can bend, stretch, warp, and curve. Gravity isn't a force acting through space and time. Gravity is the curvature of spacetime itself. This means time is physical. It's part of the universe, not something external that the universe exists within. Time is as real and physical as the three dimensions of space. And if time is physical, if it's woven into the fabric of space-time, then asking what happened before the universe existed might be fundamentally misguided. The question assumes a framework that doesn't apply. Stephen Hawking explored this idea extensively using quantum mechanics in collaboration with James Hartle, a physicist at the University of California, Santa Barbara. They proposed what's called the no-boundary hypothesis, first published in 1983. The mathematics describes the universe's origin using something called imaginary time, a concept from quantum theory where time behaves like a spatial dimension mathematically. This isn't about imagination or make-believe. Imaginary numbers, multiples of the square root of -1, are fundamental tools in quantum mechanics. In this framework, the universe doesn't have a beginning point in the conventional sense. Instead, it smoothly transitions from a timeless quantum state into the classical spacetime we experience, without any boundary or edge. Think of the surface of Earth as an analogy. If you travel south from anywhere, you eventually reach the South Pole. You can't go farther south because there is no farther south. You've reached the limit of that direction. But there's no edge or boundary there. You're still on the continuous surface of the planet. The no-boundary proposal suggests something mathematically similar for time. Trace cosmic history backward in time, and you eventually reach a boundary where time itself curves back on itself. There's no before, because time doesn't extend in that direction. Time becomes ill-defined, merging with the spatial dimensions. This creates a strange but mathematically consistent picture. The universe is finite in time, but has no beginning moment. It's self-contained, requiring no creator, violating no causality, needing no infinite past to explain. Other physicists disagree with this interpretation. Julian Barber, a British physicist and author of The End of Time, argues that time itself is an illusion emerging from the changing configurations of matter. According to his view, developed over decades, only the present moment exists. The past is just a memory stored in the current arrangement of particles, your neurons, written records, geological formations. The future hasn't happened yet, so it doesn't exist in any meaningful sense. What we perceive as time is really just the progression through different configurations of the universe. If time is emergent rather than fundamental, then asking about before the Big Bang becomes meaningless in a different way. There's no time without change, and there's no change in a timeless quantum state. The confusing and frustrating part for physicists is that both perspectives might be partially correct depending on the scale and context. At everyday scales, the scales of human life, planets orbiting stars, galaxies rotating, time behaves exactly as we intuitively expect. Clocks tick reliably, causes produce effects. The arrow of time points clearly forward, driven by increasing entropy according to the second law of thermodynamics. But at the quantum scale governing the universe's origin, scales of 10^43 seconds, the Planck time, and 10^35 meters, the Planck length, time becomes fuzzy and uncertain, just like position and momentum. During inflation, if it occurred, time likely existed in a relatively conventional sense. The vacuum energy state could persist for a duration. Space could expand over time. Events could be ordered into before and after. But before inflation, that's where our understanding completely fails. The mathematical singularity at the beginning of time in classical general relativity might be telling us that Einstein's equations break down under extreme conditions. A complete quantum theory of gravity is needed, a theory that successfully combines quantum mechanics and general relativity into a single, consistent framework.
Nobody has achieved this yet. String theory, loop quantum gravity, and other approaches offer partial solutions, but none is complete, experimentally verified, and universally accepted. Without that theory, questions about the ultimate beginning remain genuinely open. We can trace cosmic history back to the Planck time, approximately 5.4 × 144 seconds after the Big Bang. Earlier than that, our physics doesn't work. The equations give nonsensical answers. We're extrapolating beyond the domain where our theories apply. What does before even mean in that regime? What does beginning mean when time itself is quantum and uncertain? Language fails us profoundly when discussing the origin of time. Every word we use assumes time already exists. Before implies an earlier moment. Cause implies something happening first. Beginning suggests a transition from not existing to existing. But if time itself emerged with the universe, these concepts collapse into logical paradoxes and semantic confusion. Cosmologists wrestle with this constantly. They need to communicate ideas that transcend normal human experience using words built for normal human experience. The result can sound contradictory or confusing, but the confusion often comes from the inherent limits of language, not necessarily from contradictions in the physics. One approach is to abandon the notion of before entirely. Georges Lemaitre, the Belgian priest and physicist who first proposed cosmic expansion in 1927, suggested the universe began in a day without yesterday. St. Augustine of Hippo made a remarkably similar argument around the year 400 CE, claiming that time was created along with the universe, so asking what came before is nonsensical. Modern physics provides a mathematical framework for this intuition. General relativity describes space-time as a mathematical structure called a manifold, a continuous space with definite properties and potentially definite boundaries. Time could have a boundary at the Big Bang or during inflation, just as the surface of Earth has boundaries at the North and South poles. Asking what's before that boundary is like asking what color is Tuesday. The question contains a category error, mixing incompatible concepts. But here's where it gets interesting and opens new possibilities. Quantum mechanics might allow an escape from this conclusion. In quantum theory, particles can tunnel through barriers they classically cannot cross. This phenomenon, called quantum tunneling, is thoroughly confirmed. Electrons tunnel through insulators in semiconductors, making modern electronics possible. Alpha particles tunnel out of atomic nuclei in radioactive decay. It's observed constantly in laboratories worldwide. Some physicists propose the universe itself tunneled into existence from a quantum vacuum state, not tunneling through space, but tunneling from one configuration to another, in an abstract configuration space. Alexander Vilenkin, a cosmologist at Tufts University, developed this idea in detail starting in the 1980s. He describes a scenario where a universe with zero size, a geometrical point, has some small quantum probability of tunneling into a state with gun-go size. Once it makes that transition, inflation takes over and expands it to cosmic proportions. In this picture, there is no before in the usual sense of earlier moments in time, but there is a prior quantum state, the vacuum configuration space, from which the universe tunneled. Time begins when the universe achieves classical space-time properties with definite geometry. But the quantum state exists outside of time, as we understand it, not at a moment before time began, but in a fundamentally different type of existence. David Bohm's pilot wave interpretation of quantum mechanics, developed in the 1950s, offers yet another perspective. In Bohm's framework, particles have definite positions at all times, guided by a quantum potential that acts like an invisible field. When applied to cosmology through the Wheeler-DeWitt equation, this approach suggests the universe could have definite properties even at the moment of creation. The quantum potential acts like an effective cosmological constant, driving the initial expansion without requiring time to pre-exist. These ideas remain highly theoretical and debated. Different physicists favor different interpretations, but they all point toward a possible resolution of the paradox. Maybe before the Big Bang doesn't mean earlier in time. Maybe it means prior in some other sense, causally prior, logically prior, or quantum mechanically prior. The state from which the universe emerged wouldn't exist at a moment before time began. It would exist outside the framework of time altogether, in a realm described by quantum mathematics rather than temporal sequence. This challenges our intuition at the deepest level. We're accustomed to thinking of existence as happening in time. Everything we experience occurs in temporal sequence. But quantum states don't necessarily exist in time. They exist in configuration space, an abstract mathematical realm describing all possible states a system could occupy.
The universe's emergence could be a transition from one configuration to another, with time itself being a feature that emerges during the transition rather than a pre-existing stage on which the transition occurs. Philosophers have argued about these questions for thousands of years across every culture. Physics now gives us tools to make those arguments precise, testable, and grounded in observation and mathematics. We may never have a complete answer that satisfies our intuitive desire for simple causation, but we're asking better questions now, questions that can be tested against data and refined through experiment. And some theories go even farther, suggesting our universe wasn't born from nothing but from a collision in a higher dimensional reality.
Part 16. Quantum gravity and the singularity problem. General relativity and quantum mechanics are the two pillars of modern physics, both confirmed to extraordinary precision, but fundamentally incompatible with each other. General relativity, Einstein's theory of gravity, published in 1916, describes how massive objects curve spacetime. It predicts black holes, gravitational waves, and the expansion of the universe. Every prediction has been confirmed, from the orbit of Mercury to the recent direct detection of gravitational waves by LIGO in 2015. Quantum mechanics, developed primarily in the 1920s by Heisenberg, Schrödinger, Dirac and others, governs atoms, particles, and the microscopic world. It predicts atomic spectra, chemical bonds, superconductivity, and semiconductor behavior. Modern technology, from computers to MRI machines, depends on its accuracy. Both theories work brilliantly in their domains, but they contradict each other at extreme scales, where both quantum effects and gravitational effects become strong simultaneously, scales like the Big Bang singularity or the center of black holes. Loop quantum gravity, which we touched on earlier, is one of the leading attempts to resolve this conflict by applying quantum principles to spacetime itself. Instead of treating space as a smooth, infinitely divisible continuum as general relativity does, loop quantum gravity describes it as a network of discrete quantum loops, tiny units of space connected like chainmail or a woven fabric. These loops are incredibly small, existing at the Planck scale, about 1.616 10^10^5 and 35 meters for length, and 5.391 10^10^5 and 44 seconds for time. At normal scales, this discrete structure averages out, and space appears smooth, just like a television screen looks continuous from across the room, but is actually made of discrete pixels when you examine it up close. The key mathematical insight comes when you apply these quantum geometry ideas to the Big Bang singularity. In classical general relativity, tracing cosmic expansion backward in time leads to a singularity, a point where density becomes infinite, temperature becomes infinite, and space-time curvature becomes infinite. The equations blow up, physics breaks down, but loop quantum gravity says space has a minimum volume determined by quantum effects approximately 4 × 10⁻105 cubic meters. You fundamentally cannot compress anything smaller than this quantum of volume. It's not a technological limitation, it's built into the quantum structure of geometry itself. When a collapsing universe, or the backward traced Big Bang, reaches the maximum possible density, about 5 × 10^96 kilograms per cubic meter, which is roughly 10^141 times denser than an atomic nucleus, quantum repulsion kicks in automatically. The mathematics of loop quantum gravity shows that gravitational attraction effectively reverses at these densities, becoming repulsive instead of attractive. Think of it like compressing a quantum spring. Push too hard on the fabric of space itself, and it pushes back with enormous force. The collapse halts, the density reaches a maximum but finite value, then the compression reverses into expansion. The singularity gets replaced by a smooth quantum bounce, a continuous bridge connecting contraction to expansion. No infinities, no breakdown of physics, just smooth quantum geometry behaving according to well-defined equations throughout the entire process. This isn't hand-waving speculation. Scientists including Abhay Ashtekar, Martin Bogewald, Parampreet Singh, and others have performed detailed calculations using the equations of loop quantum cosmology since the early 2000s. They've simulated how a universe evolves through the bounce using numerical methods on powerful computers. The results, published in journals like Physical Review D and Classical and Quantum Gravity, show that cosmological perturbations can propagate through the bounce without being destroyed. The tiny fluctuations in density and energy that exist in the contracting phase survive the bounce transition and emerge in the expanding phase.
Information about the structure of the pre-bounce universe carries through, seeding the formation of galaxies and cosmic structure in the post-bounce cosmos. Research published in 2006 by Ashtekar and collaborators demonstrated that a pre-bounce universe undergoing slow contraction, similar to inflation but in reverse, would generate a nearly scale-invariant spectrum of perturbations. This matches exactly what we observe in the cosmic microwave background. The bounce doesn't erase this carefully imprinted structure. It preserves it, allowing patterns from the contracting universe to determine the large-scale structure of the expanding universe we inhabit. This creates testable predictions that could distinguish the bounce from standard inflation in future observations. Loop quantum gravity bounces should produce specific signatures in the spectrum of primordial gravitational waves. The amplitude and frequency distribution should differ subtly from what inflation predicts based on the different physics operating during the bounce. As gravitational wave detectors become more sensitive over the coming decades, with upgraded versions of LIGO and Virgo, the Kagra detector in Japan, and the planned space-based LISA mission launching around 2035, they might accumulate enough data to distinguish between these scenarios. The spectrum of gravitational waves from the early universe would look slightly different depending on whether it came from inflation or from a quantum bounce, particularly at certain characteristic frequencies related to the Planck scale. There's also a profound philosophical and conceptual shift here that goes beyond mathematical details. Loop quantum gravity doesn't require invoking anything beyond known physics extended consistently to quantum scales. It doesn't need extra dimensions beyond the 3 of space and 1 of time we observe. It doesn't need colliding brains floating in higher dimensional space. It doesn't need exotic forms of matter or bizarre new forces. It simply takes quantum mechanics seriously at all scales, including space-time itself, and follows the mathematics where it leads. The singularity that has terrified and confused physicists for nearly a century simply disappears. It was never a real feature of nature, just an artifact of using classical equations in a regime where they don't apply, like trying to use Newtonian physics to describe the interior of an atom. Once you properly account for quantum effects, which dominate at Planck scales by definition, the universe has no beginning or end in the traditional sense. It's a continuous process with phases of expansion and contraction connected by quantum bounce events that look dramatic from a classical perspective, but are smooth and well-behaved quantum mechanically. This resolves the ancient paradox of creation that has puzzled philosophers and theologians for thousands of years. You don't need to explain how something came from absolute nothing, because there was never absolute nothing in the first place. There was always quantum space-time structure, eternally existing, eternally transforming between different states, sometimes expanding, sometimes contracting, sometimes bouncing at maximum density, but always existing according to the laws of quantum geometry. But what about the other approach to quantum gravity? How does string theory address these questions? Part 17, String Theory and Hidden Dimensions. We experience 3 dimensions of space in our daily lives: left, right, forward, backward, and up, down. Add time as a 4th dimension, and you get the 4-dimensional spacetime of Einstein's relativity. String theory says there are at least 7 more dimensions beyond these, giving a total of 11 dimensions in the most complete version called M-theory. Why haven't we noticed them? The theory proposes they're compactified, curled up so small that we can't perceive them directly, even with our most powerful microscopes and particle accelerators. Imagine an ant walking on a telephone wire, stretching between 2 poles. From far away, the wire looks one-dimensional. The ant can only move forward or backward along its length. But zoom in close, and you discover the wire has thickness. The ant could walk around its circumference, exploring a second dimension we initially missed because it's curled up small compared to the wire's length. The extra dimensions in string theory work similarly. They exist at every single point in our familiar 3-dimensional space, but they're rolled up at scales far tinier than atoms, typically around the Planck length of 10⁵35 meters. Particles aren't truly point-like in this framework. They're tiny vibrating strings about 10⁵35 meters long, so small that even at the highest energies achieved at the Large Hadron Collider, they appear as points because we can't resolve structure at that scale. Different vibration patterns of these strings appear to us as different types of particles. An electron is one vibration mode, a quark is another mode. Photons, neutrinos, W and Z bosons, everything in the standard model of particle physics emerges from strings vibrating through these higher dimensional spaces. Even gravity itself emerges naturally from string theory. One particular vibration pattern has exactly the right properties to be the graviton, the hypothetical quantum particle that carries gravitational force. This is string theory's greatest achievement. It's the only known framework that successfully incorporates quantum gravity in a mathematically consistent way. This framework has profound implications for cosmology and the question of what existed before the Big Bang. Our entire universe might be a three-dimensional surface, a brain, embedded in this higher dimensional space. Everything we observe, stars, galaxies, light, matter, is trapped on this surface like ants on that telephone wire, unable to move in the extra dimensions. But gravity is different. Gravitational effects can leak into the extra dimensions, which might explain one of physics's deepest mysteries, why gravity is so much weaker than the other fundamental forces. Electromagnetism is about 1036 times stronger than gravity. The strong nuclear force is about 1038 times stronger. This enormous hierarchy has puzzled physicists for decades. String theory with extra dimensions offers an explanation. Gravity spreads out through all 11 dimensions while other forces are confined to our three-dimensional brain. Gravity appears weak because most of its strength is diluted into dimensions we can't access. The acaprotic model we discussed earlier exploits exactly this possibility. If parallel three-dimensional brains exist floating in the higher dimensional bulk space, and if they can move through those extra dimensions, then collisions become possible. Our Big Bang would be the aftermath of such a collision, with the pre-collision state existing in this higher dimensional framework. The collision happens in the extra dimensions, but we experience it as the sudden appearance of matter, energy, and the beginning of time from our limited three-dimensional perspective. String theory also suggests that different ways of curling up the extra dimensions, different compactification geometries, produce different physical laws in our observable three dimensions. There might be 10,500 or more distinct ways to shape the extra dimensions. Each represents a different vacuum state of string theory. Each produces different particle masses, different force strengths, different values for physical constants. This vast landscape of possibilities connects directly to the idea we discussed earlier about varying constants between cosmic cycles. If a bounce or brain collision can reset how the extra dimensions are configured, then each cycle could operate under different physics simply by having different compactification geometry. Testing these ideas is extraordinarily difficult because the energies needed to probe extra dimensions directly exceed anything achievable in particle accelerators by many orders of magnitude. The LHC can reach energies of about 13 TeV, 13 trillion electron volts. The Planck energy where extra dimensions become important is about 1019 GeV, roughly a billion times higher than the LHC. No conceivable technology could build an accelerator that powerful. It would need to be larger than the solar system and consume the entire energy output of the sun. But indirect evidence might exist in observable phenomena. Gravitational waves propagating through the extra dimensions might carry subtle signatures detectable in their frequency spectrum or polarization. Careful analysis of gravitational wave data from LIGO and future detectors might reveal these hints. Tiny deviations in how gravity behaves at small scales, millimeters or micrometers, might reveal the geometry of hidden dimensions. Experiments using torsion balances and sensitive gravitational measurements have tested this, placing limits on the size of extra dimensions. So far, no deviations from standard gravity have been found down to scales of about 40 micrometers. Experiments at the Large Hadron Collider searched for signs of extra dimensions by looking for missing energy in particle collisions. If particles or their quantum vibrations escaped into the bulk dimensions, energy would seem to disappear from our perspective, violating apparent energy conservation in our three dimensions. Teams analyzed trillions of collisions between 2010 and 2018. They found no definitive signals of extra dimensions, which places constraints on how large they could be and how strongly they interact with ordinary matter. But absence of evidence isn't evidence of absence. The dimensions might be too small or too weakly coupled to detect with current technology. String theory remains incomplete and controversial within the physics community. Some physicists embrace it as the best candidate for a theory of everything, a unified framework describing all forces and particles. Others criticize it harshly for making few testable predictions, requiring 10,500 different vacuum states that seem impossible to uniquely select between, and failing to make contact with experimental reality after 50 years of development. The debate continues with strong opinions on both sides, but the core insight persists regardless of whether string theory is ultimately correct. The universe we observe might be a shadow or projection of a larger reality. The three dimensions of space we navigate might be an illusion, a reduced representation of something far more complex existing in realms we can't directly access with our limited dimensional perception. This raises profound questions about the pre-Big Bang state. If extra dimensions exist, what role did they play in the universe's origin? Were all dimensions large initially, with only three expanding to cosmic scales while the rest remained small? Did the compactification of extra dimensions happen during the Big Bang transition itself, determining which physical laws would govern our universe? These questions remain open, with multiple competing proposals and no definitive answers yet, but they point toward a richer picture of cosmic origins than simple expansion from a singularity. Part 18, Eternal Inflation and the Multiverse. Inflation was supposed to be a one-time event, a brief period of exponential expansion lasting perhaps 10^32 seconds that set up the conditions for our Big Bang, then ended cleanly. But the mathematics suggests something far stranger and more profound. Once inflation starts in any region of space, it might never completely stop everywhere. The process becomes eternal, spawning an infinite number of universes. Here's why this happens according to the equations. Inflation is driven by a quantum field called the inflation field, represented by the Greek letter phi, in the equations. When this field has a high energy value, sitting at the top of what physicists call its potential energy curve, space expands exponentially fast. As the field slowly rolls down this potential curve toward lower energy, like a ball rolling down a hill, inflation continues but begins to slow. When the field finally reaches the bottom, its minimum energy state, inflation stops. The field's potential energy converts to kinetic energy, which then converts to particles and radiation. That's the Big Bang transition we've been discussing. In a classical universe with no quantum effects, this would happen uniformly everywhere. The field would roll down smoothly, inflation would end, the Big Bang would occur simultaneously throughout space. But we don't live in a classical universe. Quantum mechanics rules at fundamental scales. The inflation field experiences quantum fluctuations just like everything else, random jitters in its value caused by the Heisenberg uncertainty principle. In most regions of space, these fluctuations are small, and the field successfully rolls down to its minimum. Inflation ends. Those regions produce hot Big Bang conditions. But in some regions, purely by chance, quantum fluctuations push the field back up to higher energy before it can finish rolling down. In those regions, inflation doesn't stop. It continues, driving exponential expansion in that patch of space. Meanwhile, within those still inflating regions, new random fluctuations constantly occur. Most allow the field to roll down and end inflation, but some push it back up again, perpetuating inflation in sub-regions. This creates a fractal structure. Our observable universe is one finite pocket, where inflation ended successfully, about 13.8 billion years ago. But beyond our cosmic horizon, beyond the roughly 46 billion light-year radius we can observe, other regions are still inflating right now, and within those currently inflating regions, new pockets constantly form where inflation stops, creating new Big Bang universes. Each pocket expands, cools, potentially develops galaxies, stars, and life. Meanwhile, the background space between pockets continues inflating faster than light, forever separating them. The process never ends globally, though it ends locally, in individual pocket universes like ours. Inflation continues eternally in the background, spawning an infinite number of pocket universes over infinite time. Alan Guth at MIT and Andre Linde at Stanford developed this eternal inflation framework in the 1980s. It's not a speculative add-on to inflation, it's a natural, almost inevitable consequence of combining inflation theory with quantum mechanics. The implications are staggering and philosophically profound. There's not one universe. Our Big Bang is just one bubble in an endless foam of universes, each with its own history. Each bubble might have different properties determined by how quantum fields settled into their lowest energy states during that bubble's formation. The quantum fluctuations that create new pockets could also affect the values of physical constants, producing pocket universes with different laws of physics. Some pockets might have a strong nuclear force 10% different from ours. Others might have different electron masses, different gravitational constants, different numbers of particle types. Most combinations would produce sterile, lifeless universes, but some, like ours, would permit complex structure and possibly life. This naturally explains why our universe has life-permitting constants without requiring fine-tuning or design. There are infinite universes with all possible constants across the multiverse. We necessarily find ourselves in one compatible with our existence because we couldn't evolve anywhere else. It's anthropic selection on a cosmic scale. But eternal inflation also creates severe scientific and philosophical challenges. If every possible observation occurs somewhere in an infinite multiverse, how can we make predictions? Traditional science requires theories that predict what we should observe versus what we shouldn't. The multiverse seems to allow everything, predicting nothing specifically about our observations. This has led to intense debates among physicists. Some argue the multiverse makes science impossible because it lacks predictive power. Others counter that we can still make probabilistic predictions by counting which types of observers are most common across the multiverse, a controversial approach called the measure problem. Eternal inflation also has implications for the past. The Borde-Guth-Vilenkin theorem, proved in 2003 by Arvind Borde, Alan Guth, and Alexander Vilenkin, shows that any region of space expanding on average, like eternal inflation, must have a boundary in the past. Inflation can't be eternal into the past. It must have started somehow, from some initial condition, at some point in the finite past. This brings us back to the origin question we've been circling. What triggered inflation in the first place? Where did the inflation field and its potential energy come from? Possible answers include a metastable false vacuum that decayed quantum mechanically, a prior contracting phase that bounced, a brane collision in higher dimensions, or quantum tunneling from literally nothing using the Wheeler-DeWitt equation. The theorem doesn't tell us which answer is correct. It only proves mathematically that there was a beginning to the inflationary process, even if inflation continues eternally into the future. Some physicists find eternal inflation disturbing precisely because it leads to this bizarre multiverse where we can never observe or test most of reality. The other bubbles expand away faster than light. No signal can ever reach us from them. They're causally disconnected by the inflating space between bubbles. Others argue the multiverse remains scientific because it's a prediction of testable theories, not an assumption. We don't test the multiverse directly. We test inflation and quantum mechanics. If both are correct and evidence strongly suggests they are, eternal inflation follows naturally as a mathematical consequence. Rejecting the multiverse means rejecting the logical implications of confirmed physics, which seems scientifically unjustified. The debate remains unresolved with passionate advocates on both sides. But observationally, we're confined to our bubble. We can study its properties exhaustively, mapping the cosmic microwave background, measuring expansion rates, cataloging dark energy, but all of this tells us only about our pocket universe. Whether infinite other pockets exist remains unknown empirically. But the mathematics of inflation plus quantum mechanics strongly suggests they do, with new ones forming constantly as eternal inflation churns onward. And if they do exist, then the question of what existed before the Big Bang becomes even stranger and more nuanced. Our Big Bang was not the beginning of inflation globally. It was the end of inflation locally in our region. Other regions never stopped inflating and continue expanding today. Still others ended inflation earlier or later, each with its own timeline and origin. There's no universal before the Big Bang that applies everywhere. Each pocket has its own timeline, its own origin point, its own history unfolding independently. The multiverse as a whole might be timeless, pockets beginning and ending at all possible moments, embedded in an eternal inflating background that has no beginning or end globally. This is the picture modern cosmology increasingly paints. Not a simple creation story with one clear beginning, a complex layered reality where our universe is one small, perhaps infinitesimal piece of an infinite whole. Part 19. The illusion of the singularity. For decades, popular science, and even many physics textbooks treated the Big Bang singularity as a physical reality, a point where the universe was infinitely dense, infinitely hot, infinitely curved in space-time. But physicists never actually believed it was real. A singularity in your equation signals the breakdown of your theory, not a description of reality. When mathematical equations give infinite answers, infinity for density, infinity for temperature, infinity for curvature, they're telling you the framework no longer applies. You've pushed the model beyond its domain of validity into a regime where new physics takes over. General relativity predicts singularities in specific circumstances. Black holes have them at their centers according to the classical equations. The Big Bang has one at its beginning, when you trace expansion backward in time. But general relativity is a classical theory from 1915. It doesn't include quantum mechanics, which wasn't fully developed until the 1920s. At small scales and high energies, quantum effects become absolutely crucial. Ignoring them guarantees your predictions will fail catastrophically. Think of it like predicting the behavior of water. Classical fluid mechanics works beautifully for describing rivers, waves, and water pipes. But at molecular scales where individual H2O molecules matter, you need quantum chemistry. Classical fluid equations give nonsensical results at atomic scales because they're simply the wrong tool for that regime. General relativity is the wrong tool at Planck scales. The Planck length is 1.616 10^-35 meters. The Planck time is 5.391 10^-344 seconds. The Planck energy is about 1.956 10^-35 meters, roughly the energy of a flying mosquito, but compressed into a single quantum particle. These are the scales where quantum gravity becomes essential and unavoidable. At these scales, space and time stop behaving classically. They fluctuate randomly. They become uncertain. The very concepts of distance and duration lose their usual meanings in quantum foam. A singularity, which by definition requires compressing something into exactly zero volume with infinite density, becomes impossible. Quantum mechanics fundamentally won't allow it because of the uncertainty principle. Stephen Hawking and Roger Penrose proved famous theorems in the 1960s and 1970s, showing that general relativity predicts singularities under very general conditions. Their work was brilliant, groundbreaking, and earned Penrose the Nobel Prize in 2020. But it also highlighted exactly where general relativity fails. The singularity theorems tell us where we desperately need a better theory, one that includes quantum effects. Loop quantum gravity, as we discussed, replaces the singularity with a bounce at maximum density. String theory might replace it with a minimum size determined by string length scales. Other quantum gravity proposals have their own solutions to the singularity problem. The details differ significantly between approaches, but the conclusion is the same across all of them. The singularity isn't real. It was never a feature of nature. It was always an artifact of using incomplete equations. This means the Big Bang wasn't a moment when the universe sprang from absolute nothing into something. It was a transition from one quantum state to another state, a phase change in the quantum geometry of spacetime. The pre-transition state might have been a contracting universe that bounced. It might have been an inflating false vacuum that decayed. It might have been a higher dimensional brane configuration. It might have been something else entirely that we haven't imagined yet. But it was something, not nothing. There was a pre-existing quantum structure obeying physical laws. The mathematical fiction of the singularity has misled generations of physicists, students, and the public. It made the origin of the universe seem more mysterious than it actually is, a creation from absolute nothingness requiring explanation beyond physics. Yes, we don't fully understand quantum gravity yet. The theory isn't complete. Yes, the precise details of what happened at Planck scales remain unclear and hotly debated. But we know with confidence that the universe didn't begin at an infinitely dense point, because infinite density is unphysical. Nature doesn't do infinities. Math does infinities when your equations break down. This fundamentally shifts the question we should be asking. We're not trying to explain how something came from absolute philosophical nothing, a state with no matter, no energy, no space, no time, no laws, no mathematics. We're trying to explain what the pre-Big Bang quantum state was, why it existed, and why it transitioned into our current expanding universe. That's still a profound question. But it's a tractable scientific question that physics can potentially answer, rather than a metaphysical mystery requiring explanations beyond the natural world.